Hello, this is Ibrahim Nassar with Ozone Engineering. In this demo, we will be performing conducted emission simulation of a full electric vehicle. This is the electric vehicle that we're going to be simulating. As you see, the electric vehicle includes an inverter, a motor, an antenna placed on the roof, and the battery with all the cable connections. We will be using HFSS to perform the EM simulation, and then we will dynamically link the HFSS model into circuit to generate the emission report. Here's the AADT project that we will use for this demo. In the ADT project, we have an HFSS design and a circuit design. The HFSS design has the full vehicle. As we see, it's placed inside an airbox that is assigned into to a radiation boundary to model the radiation, so we can hide it. The vehicle is modeled all with kind of thin sheets uh, for the body of or the chassis of the car. It's modeled with the perfect electric conductors, the doors as well, the floor, and the motor connection. Uh, we also modeled the glass with a layered impedance boundary of a material of a glass that is already defined in HFSS. We also see an antenna placed on the top or the roof of the car that is made of dielectric and the perfect electric conductor, and it's connected, excited with a port here placed in the middle at the bottom of the antenna conductor. And we also have about 10 ports at the location of the motor and the battery to do the EM simulation. So when we take it into circuit, we can excite it with signals in circuit and do a transient simulation. The battery here is modeled in the HFSS model as a perfect electric conductor, and the motor as well. We will solve this model at zero point 0.1 gigahertz or 100 megahertz for about we set the maximum number of S's to 20 and the maximum delta S of 0.02. We also created a frequency sweep that goes from DC to 100 megahertz with about 401 points. This model is already solved, and this model takes about, let's look at the profile. It takes about 1 hour and 26 minutes on this machine, which has 24 cores, and it takes about a max memory of about 74 gigabyte of RAM. Okay, let's close this. And we can also inspect the mesh. So here I have already the mesh plot created. So if we double click, so we can see the mesh created for this geometry. We can see also plot the fields, electric fields and magnetic field in any region inside the airbox. But let's do that after we do the circuit simulation. Okay, so after the HFSS simulation is done, we want to link it into circuit. The way to do that is basically we go first and insert a circuit design project, insert a circuit design, and then here we can define a substrate, but let's just keep it none. Then what we can do basically is to select the HFSS design and drag it and drop it into circuit. And then and it will show up in circuit as an as parameter basically block with pins number that's equal to the number of excitations defined in the HFSS model. So the circuit setup is kind of a little bit large. It's already set up here. And here's the full circuit model for the conducted emission simulation. So here we see the HFSS block or the HFSS design link. If we expand the circuit design, we see it here as a component. Um, if we zoom in a little bit, so here are the pins names comes from the ports, names in HFSS, or you can modify it. So here we see at the antenna port, we connected a matching network. Then basically we terminated the antenna with a 50 ohm. To see the matching network that is designed here, we can right click on this kind of sub-circuit and select push down. And here we see the details of the matching network. Right click, and basically we can double click back again onto the main circuit design to go up in level. So here is the basically the motor is represented with an equivalent circuit of an mutual inductance and resistance. And here basically current probes are inserted, so we can plot the current at these locations in the circuit model. Here's the inverter circuit and connected with these switch devices. And here we connected also a listen component. If we double click on it, we can select different standards. And here in this example, we selected the CISPR 25 standard. Uh, at the input, we connected a 600 DC volt to represent the voltage of the battery. And then we set up the circuit simulation, and the circuit simulation here that is selected is the Nexium transient. To the way to define it, we can right click on analysis and create Nexium solution setup, and we select a transient analysis. So here's already set up. So if we double click on it here, we will basically do a transient simulation with a time sweep from 0.01 microsecond to 100 milliseconds. After the circuit simulation is done, basically we can plot the voltage versus time, and we can also look at the spectral data at any basically location in this circuit model. So to determine basically the point where we want to plot the voltage, we can just hover the mouse over that location, and you see here the net name will show up, so we can select it and plot the data. So here the AUTP basically, which is the power line. So if we can, here it's net 45. So we can basically right click and plot the voltage versus time. The way we do that, basically we right click on results, create standard report, rectangular plot, and we select voltage, and then we select the quantity. So let's plot it at the power line, which is net 45, and we hit new report. Okay, and this is the voltage versus time at net 45. Similarly, we can plot it at the listen output, which is in this case net 45 for 54. Once we put the mouse here, it's net 54. So we can similarly plot it, and which is here already plotted here in this example against voltage in millivolt versus time. Similarly, we can plot current and can right click on results, create standard report, rectangular plot, for example, and we can select current, and we will be able to plot it at the I negative and the positive at the current probe where it's defined. Here I already created that plot, so here we can look at the positive terminal of the current probe, and we see the current that goes into the motor. We can also look at the results versus frequency, and the way to do that, we can calculate the spectral out of the time domain data. To do that, we right click on results, select create standard report, rectangular plot, for example, and let's select the quantity to be at the VNet 45. Let's select it to be in dB, and let's convert that to microvolt by adding 120. And now we can change the domain from time to spectral. And let's look at it from 0.2 microseconds, for example. Can change and adjust all these options to 100 milliseconds. And let's look at it up to 1 megahertz. and we click New Report. We can also adjust this plot to view it in a better way. For example, we double click on the x-axis, then we go to x scaling, and let's change that for log scale. And here we can look at basically the spectral data. Okay, so after we looked at the emission data in circuit, we can update the excitations in HFSS and view the updated field plots. And the way to do that, basically, we can go to the circuit design and right-click on the HFSS component and select push excitations. And what this will do, basically, it will update the phase and magnitude of each of the excitations in the HFSS model. So if we go to the HFSS model and we go and open the Edit Sources window by right-click on Field Overlays and select Edit Sources, we can see that the magnitude phase got updated. So now we can take the circuit simulation data and get a feedback into the HFSS model with these updated excitations. So we can plot the electric field in the model. We can plot as well the magnetic field. And since we have an air box here in HFSS, we can also look at the radiated emissions and the radiated fields inside this air box. To summarize this demo, we basically showed an example of how to use HFSS in combination with the ANSYS Circuit tool to simulate the full electric system and identify or possibly mitigate potential sources of EMI and EMC issues. And we also showed how we can use this approach to look at regulatory standards. For example, here we use the CISPR 25. That's all for this demo, and thank you for watching.